So we are going to have two lectures again today. So I'm very happy to have Professor Emin Hafalir to give the lectures, continue the lectures on the auctions. So please go ahead.
All right. Thank you very much. I have been, so first of all, again, thank you for having me here. I am truly enjoying my time. This is my last day, I think, coming to the department. So if you want to see me after the talks this afternoon, please feel free to do so. I'm gonna, on Monday, I think it's a public holiday. So I will not come, but if you want to meet online, I'm also happy to meet. And so I'm going to present basically like 3 papers in this session, and then 2 papers in the afternoon session. And these 3 papers, they are published, and this is actually going back to my PhD years. So for the PhD students here, let me tell you some like basically context about how these papers appeared. So back in like a long time ago, 2003, when I basically reapplied for PhD programs, because my wife was doing a PhD in Penn State. I got admitted to Penn State, and I came there. Like, I think if I had stayed in Caltech, where I started my PhD, and I could have continued there, I would have worked with Federico and worked on matching problems. But I arrived in Penn State and saw that VJ is the best advisor to work with. I was an RA for the TA for a class that he was teaching about auction theory. And then there is this section in VJ's book about that kind of I skipped when I was giving the lecture on Monday, which is after the discussion about asymmetric first price auctions. Most of the stuff that he wrote in the book is about findings in the literature. But he also had a small section in the book about resale in asymmetric auctions. And this was like basically his own finding. And what he did there was kind of like criticizing like the Chicago school view about efficiency, right? So think about asymmetric first price auctions. We know that it is the equilibrium is hard to characterize, but we know that it is inefficient. So if we have a weak bidder and a strong bidder, weak bidder will be bidding more than the strong bidder in terms of the bid function. Therefore, there will be instances in which a bidder with the higher value will get the object. Lower value will get the object. So it is going to be necessarily inefficient. But the Chicago school view then would say that it's not a problem because like the market will eventually allocate efficiently. And we already know from for instance, the other similar results that we have a private information, right? So that may not work. So DJ's little section in the book was about the case whether the full efficiency can be achieved after an asymmetric auction, a 2-bidder asymmetric auction. And under like the generic result, he assumed in the paper that there is a first price auction, and then both the winning bid and the losing bid is announced, and then there is some resale, and then in this resale can we achieve full efficiency? And the answer was no. So I read that and I was very intrigued, but he actually told me that he doesn't know how to solve an asymmetric auction with resale if only the winning bid is announced. So, and then we started working on this problem, and then that was my job market paper back in 2007, and then published a year later in AER in 2008. So I'm proud of this paper. Then we had some other results about comparing first price auctions with resale and first price auctions without resale in terms of revenue efficiency. It was published a year later in Journal of Mathematical Economics. We had many little things to work on, and we had like 2-3 pages of notes for different extensions. Unfortunately, none of them turned out to be like published papers. But there was one thing that we worked on about multi-unit auctions with resale. we had some preliminary results, and years later, a PhD student of mine, started working on that, and then we got some more, results, and then we published it. Although VJ declined to be a co-author, he said he didn't contribute enough, but he actually contributed. But that was his overall humbleness. So that was, I think, published in 2012 or something. But I'm going to just talk about it only very briefly. So the main thing is going to be, the resale in asymmetric auctions with two bidders, and mostly focusing on first price auctions with resale. All right. Any questions?
Just a quick question. So if you assume the symmetry between the bidders, am I right that there's not much?
Yeah, that's right. So like, if you consider symmetric independent private values environment in a first price auction, we already showed an equilibrium, and like I think Lebrun 96 also shows that that is the unique equilibrium. So with symmetry, there is a efficient equilibrium that we characterize, and that's actually the unique equilibrium. But with any kind of asymmetry, you lose that.
I see. And if you add a resale to such a efficient auction, then
That's
the
not-
same equilibrium.
yes.
That resale will be.
Actually, there is this issue about speculation, right? That was, the Garat and Troger had this speculation idea, and like for instance, they still have symmetric bidders, but they added one more bidder who doesn't have a value for the item, but can get and sell. In that case, the equilibrium changes. But if you do not have such, if everyone is symmetric, then the symmetric first price auctions doesn't involve any resale. Actually, this will come back like in when we talk about multi-unit auctions with resale at the end, this will be actually quite relevant there too, because the things may change, and there is a surprising thing that I will say that. All right. So first of all, like asymmetries, as we have seen on Monday's class, and we will also kind of repeat here, that will result in inefficiencies that has been known since basically Vickrey. And then when there is inefficiency, there is a motive for resale. All right. So like, and also in practically, it is very difficult to ban resale. So there has been instances in which for different reasons, they wanted to ban resale, and we give two examples in the introduction of the paper, especially for like large spectrum licenses auctions. They do not want like monopoly or other concerns. So they say that if you get a spectrum, for instance, then you are not allowed to sell the spectrum to any other company. They put rules, but even these rules were circumvented in practice. So for instance, one example was that, I forgot the names, but let's call this company A and company B. Company A got the license, and according to the rules, could not sell this spectrum. But then company B, rather than buying the spectrum, bought the company. So the modeling resale is very important. So the two questions that the first paper does is the first question, which is, when in the presence of resale, how does the first price auctions and second price auctions compare? Okay, especially in terms of revenue. And the second question is, in the case that you could ban resale, like in some contexts it's not possible, but let's say that it is possible, would you want to ban resale, or would you like to allow resale, right? So you can compare these two basically contexts, auctions with resale, first price auctions with resale and first price auctions without resale. You can compare them in terms of revenue and in terms of efficiency. And in the second paper, we have some interesting results about this. So I'm not gonna do a spoiler here, but you will see. All right. So the first two papers, basically, they are under the simplest possible model that we can solve for, and actually going over this is quite difficult. There has been some papers. but not too many. And this also is because with asymmetry is quite difficult to talk about, equilibrium. So we consider two bidders, okay, and they still have independent private values, but it's not IID, it's not identically distributed. So they are independent of each other, but their values, their private values can come from different distributions. So typically there will be some strong bidder and a weak bidder, but in the first paper, actually, we do not assume, we don't have to assume strong and weak. We do not have to assume like a first order stochastic dominance. But for the presentation, I'm going to mostly focus on the case of strong and weak. Okay. So the values for bidder one is going to be denoted by like the random variable is capital X1 and distribution is F1. And for bidder two, it is X2 and F2. Bidder one will be strong bidder, bidder two will be the weak bidder in the presentation. So therefore, F1 first order stochastic dominates F2. So this would mean that bidder one is more likely to have higher values compared to bidder two. Right. So let's first refresh our memories about, in this context, what we will know about first price auctions without resale. Okay? And we know that there exists a monotone equilibrium and typically unique. There are again some papers by Lebrun and Rennie and others about uniqueness of equilibrium. And I think we did this last time on Monday's class. We have a pair of linked differential equations that involves the inverse bit function. So this is phi 1 of b is the inverse bit function for bidder 1, phi 2 of b is the inverse bit function for bidder 2. So when these two differential equations are satisfied, then the first order conditions are satisfied. So whatever are the solutions, they are potential candidates for being in equilibrium, for asymmetric monotone equilibria, where beta denotes the bit function, phi denotes the inverse bit function, and the indices denote the bidder 1 and bidder 2. All right. So this can be, it is very difficult to solve this with this generality. So if you assume any F1 and F2, there is no solution. And I think on Monday I even told you that solving this numerically is problematic too. So you use some shooting algorithms to solve it numerically. But what we know is that this phi 1 and phi 2 will be different from each other. So actually, weak bidder, this was coming from Maskin and Riley's paper, that the weak bidder is going to be bidding more for the same value than the strong bidder. All right. So we will have this kind of a picture. All right. So this is going to be like, let's denote the, here I named it actually gamma rather than beta. So let's say that this is equilibrium where gamma 1 is the bit function for bidder 1 and gamma 2 is the bit function for bidder 2. Let's say that bidder 1 has a value of x1 and bidder 2 has a value of x2. Given this equilibrium, you see that bidder 2's bid is b2 and bidder 1's bid is b1. You can see that b2 is greater than b1. So when they participate in the first price auction, bidder 2 will win and pay b2. But note that bidder 2 has a lower value than bidder 1. So naturally, bidder 2, knowing this, would want to engage in resale and try to sell it because the other bidder has a higher value. All right. So how about in second price auction? So again, like in many examples, like the extensions that we talked about on Monday, if you consider a second price auction in the context of resale, even with asymmetric value distributions, the bidding the value remains a dominant strategy. Therefore, the equilibrium of both bidders bidding their value and then the efficiency is satisfied can be observed. All right. So we will talk about, like in the later slides, I will talk to you about whether there can be other equilibria, but very very briefly, it turns out that with the presence of resale, when resale is available, bidding the value is no longer a dominant strategy. Okay, but it is what we call like a weak ex post or robust equilibrium. That could be other equilibria, but it is not a dominant strategy. Okay, so in the paper we have an example to show that, like for some strategies of the bidders, it's not a dominant strategy to bid your value.
Can you remind me, what is balance?
What is-
If our
Yeah, good question, good question. So, so we are going to, like, in a first price auction, in the main model, we are going to assume that only the winning bid is announced and losing bid is not announced. But in a second price auction, the price is the second highest bid, which in this environment is the losing bid. So in a second price auction, actually, naturally, the losing bid is announced because of the price information.
right,
Yeah. All right. So let's continue. So when, oh, okay. So this was actually a slide for comparing FBI and first price auction and second price auction without resale. Okay. So sorry about that. I kind of told you what I'm supposed to tell you in later slides earlier. But now, like, if you think about without resale environment, again, second price auction is efficient, and there could be other equilibria, but we focus on the efficient equilibrium of the dominant strategy bidding the value. And then Maskin and Riley's, like a seminal paper, establishes that, you know, there is no revenue ranking. Actually, like, this was already known by Vickrey. BJ notes in his book that in Vickrey's seminal paper, he actually considers the case in which one of the bidders have a, you know, a known value, and the other bidder has a uniform distribution. And for different known values for bidder one, actually first price auction or second price auction may generate a higher revenue. So this was already known, but Maskin and Riley's 2000 paper, they actually give some sufficient conditions for first price auction giving a higher revenue than second price auction, and second price auction giving a higher revenue than first price auction. So like, I'm going to, the next two slides will give you two examples from the Maskin and Riley characterization, or not like sufficient conditions. The first example is when the value distribution of bidder two is obtained by an kind of like extension of it, like to this, you know, on the this horizontal line, horizontal axis, then they can show that the revenue in first price auction will be higher than the revenue in second price. And the second one is when you basically obtain F2 by F1 by having a probability mass around the low values, then in this case, the second price auction will generate a higher revenue than a first price auction. So there is no revenue ranking. That's already known when we have asymmetric private values. Any questions?
what's the intuition?
I don't think they give an intuition. They just like were able to show for these cases it works out this way. Maybe they do, but I cannot tell you right now, unfortunately. Yeah. All right. So now let us go to basically our context of modeling first price auctions and second. Then later second price auctions is going to be easier. So we start with first price auctions with 3. Yeah. All right. So what is the game here? So the game has 2 stages. In the first stage, they compete in a first price auction, these 2 bidders, right? And we assume that losing bid is not announced. So actually, we also show in the paper that when the losing bid is announced, there exists no monotone equilibrium. Okay, so so when the losing bid is not announced, then in stage 2 there should be some kind of resale mechanism, and the main mechanism that we focus on in the main body of the paper is winner makes a take it or leave it offer. So like, let's say that I'm the winner, and there is incomplete information because like I know that I won. So on the equilibrium path, I will have some beliefs about my opponent's values. It cannot be higher than some particular value, for instance, but I do not exactly know, because if the losing bid is were announced, and if we had monotone strategies, then I would have actually exactly know on the equilibrium path what my opponent's value is. And if this is higher than my value, then I would just make it take it or leave it offer at that price, or that price minus that value minus epsilon, and it would have been accepted, right? So, but here now, I have the object, and there is a possibility of gain. And then in that case, actually, the optimal mechanism in this environment is a take it or leave it offer, right? So we know that from Meyerson, right? So that's the main resale mechanism that we call this monopoly mechanism because the owner actually is choosing the optimal mechanism. But we actually extend this for other resale mechanisms. I will talk about later. Yes.
So is it important that the winning bid is announced?
Winning bid for the monopoly case doesn't change anything. Yeah. All right. So this is like basically this is gonna be our result. I'm going to give more details, but let me first tell you what the equilibrium will look like, and I will basically go over how we get there in the next few slides. All right. So our result is that there is a unique monotonic equilibrium that satisfies this. So remember in the first price auction without resale, we had these two differential equations, pair-linked differential equations. Now we actually have one differential equation for each bidder. So this is for bidder 1 and bidder 2, but they are not linked with each other. Okay, two separate differential equations and the same differential equation, where basically DDB ln Fj phi Jb is equal to 1 over Pb minus B, where Pb is defined as follows. So you will see like more in the next slides, but basically this Pb is denoting the monopoly price that is chosen by the winner of the auction when this bidder wins the auction at the price of B. Okay. Okay, so this PB is going to be, of course, greater than B, and the maximizer of this. All right, and there will be a unique maximizer whenever we have the distributions, especially the weak distribution. But we assume throughout the paper that both distributions are, the virtual values are increasing. Therefore, like the regular distributions. Whenever we have regular distributions, this will have a unique maximizer, and this is the differential equation that needs to be satisfied. An important application of the implication of this equilibrium characterization is that the bid distributions are identical. So what's the bid distribution? The bid distribution is for both of the bidders. What is the probability that this particular bidder will be bidding some value B or less, right? And this is given by Fi phi I of B for each bidder. And remember, on Monday's class, I told you a result, which is that although the big bidder is bidding more for the same value in terms of bid distribution, the bid distribution of the strong bidder is first order stochastic dominating the second bidder's bid distribution, right? So this was actually not an equality but inequality. We had this, and now this becomes identical. So what we call this is like this resale symmetrizes the auction. The bid distributions become symmetric. Okay, and I'm going to give you the intuition why this is the case.
In the POV, why is there asymmetry between bidder 1 and bidder 2?
Because we assume bidder 1 is the strong bidder, bidder 2 is the weak bidder, right? So bidder 1, when bidder 1 wins the auction, he knows that bidder 2 actually will have values smaller than his, so he will not even bother making a monopoly offer. Only bidder 2 will make a monopoly offer. But actually in the paper, we have this as I and J, and I and J can change where the values are. So we will actually, like in the presentation, I assume this kind of a distribution, F1, F2, and therefore only bidder 2 will be making an offer to bidder 1. Whenever bidder 1 wins, bidder 1 will not make an offer. Whereas in the paper, we also allow for these kind of distributions. So this is like F1 and this is F2. And in this region, basically bidder 1 will be strong, and in this region, bidder 2 will be strong, and then we will just switch the indices. But for the presentation, I'm just writing this way. Okay. Yeah.
Sorry, so could you define strategy again?
The strategy is like I'm gonna do that in the next slide. Basically, the strategy is gonna be first of all, since this is a two-stage game, right?
Right.
It should be defined as what is my behavior in the second stage and the resale stage. In the resale stage, it's gonna be if I'm the winner, then given the information, which is like if I'm the winner, I know my I know my bid, but I do not know my opponent's bid. What price I will choose. And for the loser, it's gonna be easy. For the loser, loser will just obtain a take it or leave it offer of a price, right? So
Yes,
sequential rationality requires that I will accept the offer if and only if this price is lower than my value. That's the strategy. And given these strategies in the second stage, the first stage strategies will be just like how much to bid given my value.
Okay,
Yeah.
so in this first line, so you
It's like
characterize.
pi is only the inverse bid function. So in the first stage, we have only the bid function as a strategy, right?
Right. So is this characterization of equilibrium only in the first stage and
Yes.
not about the second stage?
Yeah, second stage, I think I will tell you a little bit more in the next slides, but the second stage, we of course start solving the game with the second stage. But in the second stage, nothing interesting is happening. Like the loser's strategy is simple, except the offer if and only if this price is lower than my value, and the seller's, like the winner strategy, is also choose the optimal monopoly price. All right, so, but another nice thing is that actually, this also will come in a nice picture, and it's actually, luckily, this is like a geometrical interpretation. I like geometry. That, given F1 and F2, which are two different distributions, since the resale symmetrizes the bid distribution, then you can think about a hypothetical market in which both bidders are getting their values from the same distribution, and that symmetric first price auction actually results in the same bid distribution. We call this F, symmetrizing F, and this actually has this kind of an interpretation. This is not actually like in closed form in a sense that F appears here and here, but you can like at least numerically solve this very easily. Like it's like a fixed point kind of a thing, but it has a very nice geometric interpretation. So if you use this F, then you can actually write down the revenue in the first price auctions with resale in a very simple form. This form, all right? 1 minus F of P squared dP. Okay, let's continue. I'm going to give you a little bit more information about basically how we solve. And as Koji asked previously, so we need to start with the second stage. Let's start with the resale stage. So let's say that, okay, so I'm gonna go back to like weak and strong. So this is, these are my value distributions. F1, F2, and these are gonna be my bid functions. This is beta 1, and this is beta 2. And the inverse of it is gonna be denoted by phi 1 and phi 2, all right? So bidder 1 will be bidding less than bidder 2 for the same value. So let's say that bidder here, like, just assume this J is equal to 2. So let's say that bidder 2, all right, has a value, so this is B, and this is, or just actually call this I and J to make it consistent with what's written there. So this is phi J of B, right? So bidder 2 has a value of phi J of B, bid B in the auction, and now knows that the fact that the winning tells you is that bidder I's value is less than phi I of B, right? Because if bidder 1's value were greater than phi of B, then I would have lost. So then what is my optimal monopoly price? It is the P in which, so let's say that this is P, right? If my opponent's value is here in this interval greater than P, but smaller than phi IB, because the fact that I won means that it has to be smaller than phi IB. If it is in this interval, then I'm going to get PV. I'm going to basically the monopoly price will be accepted. And if it is smaller than phi J of P, then the monopoly price will be rejected, and I will keep the object and enjoy XJ. All right. So this is my maximization problem. Fi of phi IB minus Fi P. This is the probability that the price is accepted times the price plus the probability that the price this will be rejected, and then times XJ. So here I said something wrong there, but you understand it now. All right.
Sorry, what was XJ?
XJ is the value of bidder J.
Value of beta.
Oh, yeah, and then I kind of like, since B is already sunk cost, I ignore it, right? Yeah. So when you like, this is a simple monopoly, pricing problem. So when you differentiate this with respect to P, you get this. And this is not surprising. This is like this looks like a virtual value truncated at F. Like if this were one, this would have been exactly virtual value, right? But this is not one because like basically the upper limit of the possibilities actually start from Fi pi ip. And when the Fi is regular in Myerson's sense, when the virtual value is increasing, then this will give you a unique solution, and that will be your maximizer. And we assume regularity, so this characterizes basically the optimal P given the equilibrium bit functions in the first stage, or the inverse bit functions phi I and phi j. All right. Now, let's basically, given this behavior, now let us go back to the first stage and characterize the equilibrium behavior, right? So pick some B and suppose that phi j is smaller than phi I, exactly here. Phi j is smaller than phi I, right? So there is gains from trade, and j is gonna be now the seller, right? Because j will, let's say that we consider a j whose value is xj, which is equal to phi jb, all right? And wins the auction at the bid of B in the first stage. Then this is like basically this is the same part that I had in the previous slide. Now I'm also including the payment to the auctioneer, right? So with probability Fi or phi I of B, I am going to win, and then in that case, I'm paying B to the auctioneer. So then all you need to do is take the derivative of this expression with respect to B and equate to 0. That's going to be a necessary condition for a local optimizer, right? So when you do that, you get this. Okay, so there is some math involved, but just basically the optimality of PB in the previous slide makes this much more complicated. Some things will cancel out, and you will get this simple expression. I will actually tell you intuitively why this is the case. So you don't have to do the math even, like, because there is an intuitive reason that, both bidders will have the same differential equation. All right. So this was the equilibrium utility calculation characterization for the weak bidder, who is going to be the seller in the resale stage. Now let's do the same exercise for the strong bidder, who's going to be a buyer in the resale market. All right. So strong bidders, remember, this is the strong bidder's bid function. So when strong bidder wins the auction, then there is no reason for sale because he knows that other bidders value smaller. But when bidder one loses the item, still he can get a positive utility, because in the resale stage, maybe a price that is lower than her value will be offered, and they will, like this strong bidder will keep the rest. So,
can I?
Yeah.
So, in the expression for the seller's payoff,
Yeah.
is XJ.
Yes.
Why doesn't it appear in the grid?
So here it cancels out. So basically from here, right? So we use this here, and then it just cancels out. Like actually, XJ in equilibrium will be phi JB anyway. So like we could have written this one as like in equilibrium is gonna be like basically you can substitute in the first order condition as phi JB. That's one reason, and another one is actually this equation.
Yeah, but phi J does not appear either, right?
Yeah, it doesn't because of the because of the cancellations, and I'm going to tell you intuitively. You will understand it very nicely with the intuition, because this is a very simple intuition. So let's do the same thing for the now the strong bidder, who will be the buyer in the resale market. First of all, when this strong bidder wins the auction, there is no extra benefit, right? Because like with probability Fj phi JB, so let's say that my value is here xi, and then I win with a bid of B. I know that the weak bidder's value is somewhere here, so I'm not going to even bother making a monopoly offer, and then I will consume the object. So with probability Fj phi JB, I'm going to consume the object, and my utility is x minus b. But when bidder J is value is greater than pi JB, so I'm gonna lose actually, then there is a possibility that I will get the extra benefit. What is this possibility? So for each xj value, right? So there is going to be a p of beta j of xj. So remember, beta j of xj will give me some bit, right? And p is a function on the bits. And I am going to accept this if and only if this value is positive, right? So I'm not going to accept a non-profitable offer. So this like bracket with a plus means that minimum of this and 0. I'm sorry, the maximum of this and 0, right? So, and again, when you take the derivative of this with respect to b, we can do it here, but I don't want to bore you with the math. This will result in the same differential equation, and there is a reason for this in the next slide. Okay, sorry, one more slide. So let's before that, then due to these basic results, we established 2 results. One of them is that in the appendix we actually show that this differential equation is not only necessary but also sufficient. So like I told you, like in last class, that most of the papers actually in ocean theory, they do this first order approach, right? So they say that let's assume a symmetric and monotone equilibrium exists. Therefore, if an equilibrium exists, these differential equations needs to be satisfied. But in the appendix, we actually show that this is also sufficient. So this differential equation that applies to both bidders is a necessary and sufficient condition for equilibrium. And this immediately implies that there is a bit symmetrization, because both, so like going back to here, right? So we have written this for I, and we have written this for J, and they satisfy the same differential equation. They will have the same initial condition, which is like bit at 0 is 0. Therefore, they will be the same function distribution. All right. So this is symmetrization. And now let me tell you why the symmetrization holds intuitively. Okay. So
you can know about the distribution different than
so we assume, okay. So throughout the paper, we assume that the lowest value is 0 and highest value is W1 for bidder 1 and W2 for bidder 2. So we did not consider the low values to differ. So we don't have a formal result that this result holds for other cases, but I think it can be shown. So like I don't think, like basically the initial conditions that the initial conditions is gonna be the lowest valued bidder's bid is 0, not like the 0 valued bidder bid is 0. So I think that the result will hold. Okay, so now let's think about the intuition. So in terms of getting an intuition, thinking about the marginal gains is the best way to go. All right. So actually, let me go back to like the without. Okay, so this is the without resale equilibrium strategies, and why does basically this part appear here? Like think about bidder 1. Okay, so now let me draw something like this is bidder 1's bid and this is bidder 2's bid. This is bidder 1's bid, this is bidder 2's bid without resale. So think about bidder 1 or bidder 2 who is thinking of increasing the bid just a little bit. Okay, rather than bidding B in equilibrium, let me consider bidding B plus epsilon. So there are pros and cons of this, right? The con of that is that whenever I get the item, I'm paying epsilon more. But the pro of that is for the values here, like just around here, which is around phi j of B, for those guys, I am now getting the item and paying B, right? So for this small interval, I get an additional benefit of pi JB minus B. And that's why this appears here. But now with resale, this is different because of the resale institution. And this is what I will show you with symmetrization. Okay. Okay. So now consider a change from B to B plus epsilon. So this is the idea for without resale. But now think about this with resale. So now let's first consider the big bidder, who is going to be the seller, right? So for the seller, okay, so now let's say that this is like an auctions with resale. So all these guys, right? I am going to now win against them. But for all those guys, I will be actually sell to them, right? Because basically these are going to be in the interval that the resale price will be accepted. So for all the additional people that I get, these are the highest possible values, and PB is going to be necessarily smaller than those values, and all of them will accept my monopoly price. So my gain becomes not pi I minus B, but P minus B. So this is like clear, maybe easier to see for the seller. But now let's think about for the buyer, the strong bidder. So for the strong bidder is actually before the change and after the change. So before the change, for for this additional small measure of people here, all right, by increasing, okay, I was actually still getting the item. So I was losing against them. But those guys actually were making offers that is acceptable to me. So I was actually getting at the price of P. Now, by bidding slightly more, I'm going to directly win against them and will get at the price of B. So the additional gain is the XI minus B minus XI minus P, which is also PB minus B. Okay, so this is also like nicely depicted in the here. So basically, for this is bidder 1, this is bidder 2. So the by increasing slightly from B to B plus epsilon for the buyer in the auction part, I used to still get at the price of PB. Now I get at the price of B. So that's my gain. And for the seller, I used to not get it, but now I get it, and I will not only get my value, but I will actually get P. So P minus B is my gain. So for both the strong bidder and the weak bidder, the marginal gain is the same. Okay. So I hope this was okay. Okay. So also in the appendix, he also showed that when we consider monotone equilibria, the equilibria that we characterize is the unique one. So there is no other equilibria. And as I mentioned earlier, it is important that the losing bit is not announced, because otherwise we can show that there exists no weakly monotone equilibrium. So like in BJ's book, sub chapter 4.7 or something, like when he talks about the case in which the winning bid and the losing bid is announced in a first price auction, and shows that there exists no efficient equilibrium. He doesn't show that like whether other equilibria exists, and we were able to show that there exists no other equilibria in the appendix. All right. So now, after solving the first price auctions resale equilibrium uniquely, now let us have some calculations about the revenue in first price auctions with resale. And it turns out that we can, as I mentioned earlier, we can consider a hypothetical distribution function that satisfies this equation. And again, this equation is not like, I don't have F on the left side and F1 and F2 on the other side. It's not as good as we expect, we hope, but still, like it is in a way closed form, right? For an F that satisfies this, and this is uniquely defined as long as the distributions are regular, it turns out that the revenue in a first price auction with resale for value distributions and F1 and F2 is equal to the revenue in a first price or second price auction with symmetric distributions FF, and this revenue is given by this simple formula. All right. So now let's move to the second price auction. Okay, so before that, I also told you that this has a nice geometrical interpretation. So what is the geometrical interpretation that we kind of really liked is the following. So let's say that this is F2 and this is F1, and here I allow for actually, no weak and strong. This can be arbitrarily crossing each other. Doesn't, we don't have to assume that. So now let's look at in this region, F2 is below F1. So what I'm going to do is for each P, I'm going to look at the intersection of this P and F2 curve, and I'm going to do a tangent of this, okay? And then what I'm going to do is I'm going to take a mirror image of this tangent line to this side and find where does this line intersect with F1. And then I go horizontally over here and find the intersection point of this P and here. And that's going to be my, basically, F value at P. So it has a very nice geometrical interpretation. If you do this for all P, then you will get F. All right. And so that's something that we liked. This doesn't give us anything, but it's just like a nice. So now let's talk about second price auctions with resale. So as mentioned earlier, you asked this question that what is known in a second price auction, and of course losing bid is natural known, because when you participate in second price auction, how much auctioneer charges you will be the second highest bid, right? So the losing bid is known. And as I mentioned earlier, it is no longer a dominant strategy to bid the value, all right? But what we can show is that bidding the value is an equilibrium, but also it's an equilibrium for all value distributions. And there is this discussion about like ex post equilibrium, weak ex post equilibrium, and there is less known something like called robust equilibrium in this, not in the robust mechanism design sense, but there is a robust equilibrium definition by Tillman Burgers. So it satisfies those requirements, and there is no other strategy that satisfies those requirements. So it is a unique robust equilibrium. So it's not a unique dominant strategy equilibrium, but it is the unique robust equilibrium. And robustness, you can think about this as like there could be some other equilibria, but these equilibria may only satisfy to the equilibrium for some particular F1, F2, but it will not satisfy the equilibrium for some other F1 and F2. Whereas bidding the value is an equilibrium for all F1 and F2. All right. So we focus on, yes.
Sorry, so is the fact that it's not there's not an answer G is like easy to see here.
Okay, so let me try to remind myself. So why it is not a dominant strategy to bid your value? So
like in the resale, say some your opponent may do something really crazy.
no. It's like we still focus on sequential rational equilibrium. So we do not allow for sequential irrational behavior. But what was it? It was something simple, but it was like basically like this was when throughout we assume sequential rationality, but even with sequential rationality, there are instances in which the bidding the value is not a dominant strategy once resale is considered. But I will tell you it's
Sequential rational study, do you mean that in the second stage people will be
optimally? People behave optimally, but in the first stage, the bidding the value for some strategy of the bidder one, it's not a dominant strategy for bidder two. But I should have checked this before coming here. It is in the paper, but it's not a difficult example. It's just like an example. All right.
Why there's no equilibrium where the beta one always bid one and beta two always bid zero? But it violates robustness or in the second price auction with that.
No. So bidder one bids always one and bidder two always bids zero. Okay. Just a sec. Yeah. So that should be a reason. I remember we even told about this. And also like there is a proof in the appendix of the paper that kind of shows that this is the unique robust distribution. But let me actually go back to these two things after like during lunchtime. All right. So but we focus on this robust equilibrium of bidding the value, and therefore the auction is efficient, and therefore there will be no resale stage, and therefore second price auctions resale revenue is going to be the same as second price auctions without resale revenue, and it can be given as follows. So like basically with asymmetric value distributions, the revenue is equal to the expectation of the minimum of the two random variables, and this is given by this formula. Now let us go to our main result. I'm going to give you like I'm going to give you like the general proof first, but then I will give you like a less general and analytical proof later. Okay, so but what's the result? The result is we don't have to assume anything other than the regularity of the distributions, which is a mild assumption. So suppose that both distributions are regular, then it turns out that the revenue from a first price auction with resale exceeds that from the second price auction with or without resale. So this is actually like to us very surprising, and like there should be some kind of intuition, but we don't really have a good intuition, and this is surprising because it turns out basically for the same setup, two bidders, private values, asymmetric value distributions, there is no general revenue ranking, right? The first price auction or second price auction can be better depending on the value distributions. But once you complicate the model with adding resale, somehow magically the revenue ranking is there. So always first price auction with resale is better, right? So
price adding first price auction without resale.
yeah, so that's gonna come in the sixth stage. So like we have a conjecture, which is we were not able to prove. So for some PhD students who are still interested in this consequence, it's still an open problem, that we have a conjecture that the first price auction with resale is actually better than first price auction without resale. So if that's the case, then we can actually get some partial results, right? So but we still like the second paper is going to be about some sufficient conditions for that to be true, and we were not able to find any counterexample to it, so it's still a conjecture and an open problem. All right, so like so let me tell you, so do we have any PhD students here? Only one? So a couple. So let me tell you that basically the story of this the next slides, basically, in which we will use counts of variations to prove this general result. So we first got the symmetrization results, and then neither BJ nor me are very good at computational methods and using MATLAB and those kind of stuff, but we were still using this like MuPad or MATLAB feature in scientific workplace to do. And then we were trying examples, so like our
Excel.
yeah, learn Excel. So now with ChatGPT, we don't need to know anything. We can just ask it. Sorry for those kind of stuff. But anyway, so we were we realized that we are able to find the revenue in first price auctions with resale, and we were comparing it with second price auction and second price auction with resale, expecting some stuff like for some values one is going to be better, for some other values it's going to be, but no matter what we try like asymmetric uniform, some power distribution, some this and that, it was always like first price auctions having a higher revenue. And then we got some like a partial theoretical results that will come in 2 slides about, like, for instance, when we assume like F1 is convex, then you can actually get some like nice things, and you use like some arithmetic mean greater than geometric mean inequality at the end, you get the general result. But we were not able to solve it, and actually as a PhD student, like I actually worked on this problem 8 months. So there was this one inequality that I needed to prove. And like I did not work on, like VJ of course was working on it, but I was like solely working on it because VJ also had some other papers too, right? So I just solely tried to prove this inequality for 8 months without stop. And I think like in the last 3-4 months, we realized that this is a calculus of variations problem. I had no idea about what calculus of variations was, but this, of course, is a very well-known method in physics and in math, right? So like when you are trying to minimize or maximize a function, and then there is something called Euler equation. And so like in the last couple months, I learned about calculus of variations, and then somehow magically, the proof was there. But this was like after 8 months, right? So like we first prove it for monopoly resale mechanism, then we extended for monopsony resale and random proposal mechanism and sure trade mechanisms and so on, like in the extensions part of our paper. But I'm going to focus on just like what's the calculus of variations. Calculus of variations, at the time that we used it, actually, we were not aware of other economics papers were using it. So what's the idea in a calculus of variations? So what we want to say is that, like, think about geometry. Okay, so what I want to say is that I had this, this is f given geometrically by f1 and f2, and the revenue in a first price auction with resale is simply integral 1 minus f square. All right, whereas in a second price auction, it is integral 1 minus f1 times 1 minus f2. So it's actually quite simple. And you know that when f1 and f2 gets closer to each other, f becomes equal to f1 and f2. So the calculus of variations method is something like, basically, you take a perturbation on, for instance, you fix f2 and you do a perturbation on f1. So rather than thinking about f1, you consider f1 a convex combination of f1 and f2 with epsilon, where epsilon is small. All right, so f1 gets a little bit being closer to f2. And if you can show that once you do this perturbation, the revenue difference between first price auctions with resale and second price auctions with resale decreases. If it is monotonely decreasing, like if it's a negative derivative with respect to epsilon here, then we know that at the end it's going to be 0 because they are the same. So f1 and f2 and f, they coincide. That means if the derivative is negative, then it will mean that for all other values, it's going to be positive. And therefore, the first price auction with resale will have a higher value than the expected revenue than this second price auction.
Sorry, can I?
Yeah, so if you
for-
have this kind of a sheet, yes.
Sorry,
Yeah, let me go back.
You are moving F1
Yes.
closer to
F2
I see.
with the convex combination. So like consider F1 tilde equal to 1 minus epsilon times F1 plus epsilon times F2.
I see.
And then basically once you are doing that, you use Euler's methods like calculus of variations because you are making functions closer to each other. And then there is an expression for.
You're moving only F1 closer
Yeah.
to F2, but F2 is unchanged.
Yeah, yeah.
I see.
Yeah, for this example.
Yeah, maybe it's a stupid question, but I was a bit stupid. That you are moving just one of the functions while the other one is being fixed, and still you can somehow say that the revenue becomes closer to something in the middle.
No, it's basically okay.
It's important that you are moving F1 and not F2, or it could be.
I remember it, like again something that I need to go back to the appendix and see. But I remember that it is like this picture you suggest me that we were fixing F2 fix. I don't think we were fixing F fix, so that would have been your conjecture. No, so basically so in order to show that like let us look at this next picture, right? So the next picture is something like F2 is approaching to be F1. And we are basically writing down for all fixed F1 values, we are changing F2 and looking at whether the revenue difference is positive or negative, right? And we show that it will have this kind of a shape because it is actually there is this problem here at the end, but that's not a big issue. But basically, it's a monotone decreasing function. So therefore, tell me any F1 and F2 that you like. Because of this picture, I know that this F1 and F2 will have a positive difference. So I don't think you would need to fix F. You can fix either F2 or F1, doesn't matter. You will always get the result.
Is delta?
Sorry?
What is y-axis? Delta?
Delta, okay, so this is the expected revenue difference between first price auctions with resale and second price auctions. Actually, yeah, so you are looking at the difference between the revenue. All right, so very quickly, sorry. There's I think I have only 30 minutes, so maybe I may skip this, but this was one of the earliest the first couple months, we were able to show that when F1 is convex, then this nice inequality holds. Okay, and then you substitute some things about like you change the variable to be a z, and then you can write this g, which is like another hypothetical distribution. Right? Remember, like we have this f, which is hypothetical distribution. Now g is another hypothetical distribution, but g satisfies something, and then at the end, using this g and using arithmetic mean greater than geometric mean inequality, we were able to show this like analytically. But I'm going to skip this one time. All right, so like now I'm ending my main presentation for the first paper. 2008 AER paper, that the findings are that although without resale, no revenue ranking is possible, once resale is considered, the revenue ranking is established, and always first price auction generates a higher revenue than second price auctions. So like this is our one-liner, which is like sometimes adding a real world feature simplifies the theory.
So have you checked other auction formats?
Sorry?
Have you checked other auction formats than first price or second price?
So I will tell you about the extension set. Yeah. So we considered like first of all, like the obvious questions about what happens when we have more than 2 bidders. I'm going to discuss that, and then we consider like still the same auction format, like and with 2 bidders, you know, the first price and second price auction are the most natural ones, right? But we also extended for like affiliated private values, and we have a few extensions. Like I think in like 20 minutes or so, I will be able to tell you. But we have some 2 or 3 pages about those things, but most of them did not turn out to be papers. They were.
Did you find anything that's better than first price auction?
So we did not solve, like for instance, for like optimal auctions. So there is this optimal auctions with resale paper, but it is like done by Charles Zane, econometric paper. But this is done in a very different setup. Again, this speculation zero value setup. No, we are not aware of any like an auction that is like better than first price auction.
Also, this optimal auction problem in this setup is still open. Yes.
Yeah, I think so. Yes. Yeah. So.
By the way,
Yeah.
so in general, so it appears that the left-hand side is first price auction with resales weekly have a weekly larger
Yes.
revenue, and is it actually strict for the generic, some kind of generic case?
Yeah. So basically, as long as they are not identical, so like if F1 and F2 differs, this is strict.
Oh, I see that.
If F1 and F2 are the same, this is the same. So now the second paper published a year later. So we were looking at so now rather than comparing in the presence of resale, how does the 2 auction formats, first price and second price auction, compare? Now let us look at the other question. If you are gonna use first price auction, is with resale environment or without resale environment better? And we can ask these questions in 2 dimensions. One of them is revenue, other one is efficiency. All right. So, and we have this conjecture still not proved. So we will have partial results to show that first price auction with resale revenue is greater than first price auction without resale revenue. For 3 family of distributions, we proved this in the paper. I'm going to talk to you about it. And but like we don't have any counterexamples yet, or nobody has shown us any counterexamples yet. So and if this were correct, for instance, if there is a proof for this, then we know that first price auctions with resale is better than second price auctions with resale, which is equal to second price auctions. All right. So if second price auction is giving, like for the cases in which second price auction is giving a higher revenue than first price auction, for instance, some cases that are identified by Maskin and Riley, then this conclusion will automatically hold. All right, but let's continue. And what are the results in our next paper? We consider the only known basically families of distributions in which we know an analytical solution to the pair of linked differential equations to first price auction with ERATO resale, right? Remember, I told you that we have this pair of linked differential equations, which is difficult to solve, but there are 3 papers, one of them earliest by Plum, and Chen has 2 other papers, which gives like some family of distributions such that this linked differential equations has a solution. Therefore, you can actually characterize an equilibrium without resale. All right. For all the cases that a closed form expression or some kind of closed form expression is available for first price auctions without resale, we were able to show that the revenue is higher with resale compared to without resale. And this is like our surprising result, which is that for the social surplus comparison between with resale and without resale, there is no general ranking. And why, like, this is like even going against even this intuition that like once you allow for something something that allows for ex post trading, that should be of course good for the society, but this doesn't take into account the behavior change due to the context, right? So it is obvious that when you compare a first price auctions with resale environment and compare the social welfare after the auction and before the resale and after the resale part, of course, after the resale part will generate a higher social surplus, because whenever the trade is taking place, it is increasing the social surplus, right? Because this is beneficial for both parties. But what we show in the paper is that due to this anticipation of resale, the result in the auction, okay, may be so inefficient that the efficiency gains done by resale is not high enough to compensate the inefficiency due to the presence of resale. So this is the surprising part, that actually resale may hurt in the social welfare. Like when you compare first price auctions without resale, that may actually in equilibrium may have a higher surplus than first price auctions with resale. And that's what I want to basically show you in the next 15 minutes. All right. So I told you that there are 3 distribution families in which we know a solution to the pair of linked differential equations. The first one is kind of like a generalized power distributions. So basically, I think in the past, it was already known to solve asymmetric uniform distributions. We actually had, like in VJ's book, has a characterization of it. I was hoping to do it on Monday, but I didn't have time, so I was not able to show you. So once you have like 2 uniform distributions ending at W2 and W1, then you can actually, in closed form, solve the equilibrium bit functions and equilibrium inverse bit functions. What Plum has done in his paper is that generalize this to power distribution. So now you allow for this kind of distributions or this kind of distributions. So they have the same power. They have the same power. A can be anything, but they are defined over different intervals. So here, typically like W1 is greater than W2. So W1 is the strong bidder, W2 is the weak bidder. So for this case, a solution to the differential equation exists for auctions without resale. Second one is by chain, and this one is like again, power distributions, but it allows for two different parameters at the power part, but requires some inequality. It's some equality to be satisfied. So it can, like, one of them can be like a uniform, other one can be power, but they need to satisfy some conditions. So for both of these families, there are basically 2 degrees of freedom. So here you have I'm sorry, 3 degrees of freedom, A and W1 and W2. Here you have A1, A2, W1 and W2, but they need to be satisfying some conditions. So again, 3 degrees of freedom. And the third distribution again by Chen was kind of like a exponential and power distribution combination, but over different intervals. So like strong bidders value distribution is between 1 and A plus, A plus, A1, and the big bidders value distribution is between 0 and A plus 1, but actually big bidder has a probability mass at 0. All right, so for this case, actually the solution for the pair of linked differential equations is possible. So our first result is that for these 3 family of distributions, the first price auction with resale gives you a higher expected revenue than without resale. For the first plums case, what we do is actually, so I'm not gonna like do all the details, but you can look at the distribution of revenues, the selling prices. Distribution of selling prices given by the product of F1 and F2 combined with the inverse bid function, and N here represents no resale case. So once you do this distribution of revenues denoted by L for no resale, you get this expression for the no resale case and this expression for with resale case. And actually you can show that there is a first order stochastic dominance. So since there is a first order stochastic dominance for the price distribution, revenue distribution, this is not the case for the bid distribution, but it is actually turns out to be the case for the price distribution, then you automatically get the revenue ranking. The second and the third one is something that is like hypothetical, the hypothetical distributions, right? So the same method doesn't work for chain 1 and chain 2. So for this one, in order to show that we consider the G, the BD distribution such that a symmetric FPA in which both bidders draw values from G is revenue equivalent to an asymmetric FPA. Okay, so then like this is different from the F that we defined earlier, because in the F that we defined earlier, that was in the context of with resale, right? So this is for like basically find, like consider the like the price distribution again, all right, for asymmetric auctions without resale, and find the G such that it will have the same price distribution. And then it turns out that for that G, there is a first order stochastic dominance, so you are done. So this is the proof method. It's a little bit like nitty-gritty, but it works for both cases.
That's partly because if stochastic dominance is G,
Yes.
they tend to be
Yeah.
more.
So basically, like the expected selling price is nothing but the expectation of the price distribution, right? And then if the price distribution is better in terms of stochastic, first order stochastic dominance, of course the revenue will be higher.
So if you compare the bid functions,
It doesn't, yeah, if you compare the bid functions, it doesn't give us results. So like some.
yeah, but do you know how the bid functions compare between with resale and without resale? Is it like the weaker it's more aggressively also?
Yeah, I think it should be. I don't think we have like a a proposition about it, but yeah, it makes sense. So like since like resale gives you like if you are a big bidder, you have more reason to be more aggressive. So that's why like basically the bid distribution being symmetrized with resale is due to that reason, right? So like in without resale, the strong bidders bid distribution is the better one. With resale, they become equivalent, and the reason is because basically as a weak bidder, I now can like I do have more chances because I can sell later, right? So like my guessing is like the reason that we needed to work with the price distributions rather than the bid distribution is that for the strong and the weak it actually is the reverse between with and without resale. Good point.
And for the strong bidder in software,
So for the strong bidder actually tend to be they will be lower. Yeah. All right, so let's continue. I have 15 minutes. So now let's think about the efficiency. So for what is the social welfare? So the definition of social welfare is the sum of the utilities of all bidders and the auctioneer. So the transfers doesn't matter. All I care about is the resulting allocation, right? So without resale, so this is, let's say that this is beta 1, this is beta 2. So for any given x1, so let's say that this is x1. Okay. If bidder 2's value is smaller than phi 2 of gamma 1 of x1, so here gamma is like, gamma is the bid function and phi is the inverse bid function. So phi 1 of x1 is the bid of bidder 1. Gamma 1 of x1 is the bid of bidder 1. And phi 2 of gamma 1 of x1 is the value of x2 who would bid B in the auction, right? If bidder 2's value is smaller than that, 1 will win, and I'm going to write x1 here. Otherwise, 2 will win, and I'm going to write x2 here. So this is like a simple for the social welfare calculation without resale. But with resale, it's a little bit more complicated because I need to write down the allocation at the end of the game. So the game is there is an auction, and then there is a resale stage, and then we write at the end. So there are now 3 regions that I need to think about. So now there is going to be some kind of like a resale stage here. So there is going to be some P function here, right? So again, since I'm here the variable is x1, which is the strong bidder. What I'm going to do is whenever 1 wins, there is no resale, right? So this is the condition in which 1 wins, and there is no resale. And now when 2 wins, there are 2 parts. One of them is 2 wins, but 2's value is not high enough to make the price greater than x1. Therefore, the resale will take place. In that case, actually, I will still write x1 rather than x2. So this is the condition for making sure that 1 loses, but this is the condition that the 2's value is not, basically, this is the value in which the 2's price is exactly x1. Okay. For any value greater than this, the price chosen by 2 is going to be greater than x1, and therefore there will not be any resale. And therefore x2 will keep it. And in this region between this and that, the 2 wins but resells to 1. So we have these three expressions that needs to be added up. So, but then you can actually combine the first 2 because this is the same as this one, and inside is the same as this one. So these 2 things will just become 1, and this becomes our social welfare. Okay. Now let's do some like a little bit of analytical result first before basically I'm going to tell you like the intuition for our main surprising result. Like now let's fix W2 to be 1 without also generate for the Plum's case, and for arbitrary A and for arbitrary W, what you can show is that for arbitrary A, we get a necessary and sufficient condition for first price auctions, revenue ranking between like the first price auction with revenue with resale and first price auction without resale surpluses to be greater than each other. So basically, this gives you some kind of like a characterization. And for instance, if you take A equal to 1, which is uniform distribution, it turns out that the second price, the surplus under first price auction with resale is smaller than the surplus under first price auction without resale, if and only if W1 is smaller than an amount which is approximately 2, so 1.95. So what does this mean? What does this analytical result means? It means that when the asymmetry between the two bidders are not that big, okay? Like for instance, like the value distribution for bidder 2 is between 0 and 1, and value distribution of bidder 1 is between 0 and 1.75, for instance, then the resale actually is helpful for the surplus, right? But when it becomes too asymmetric, if the highest value for bidder 1 is 2 or 3 or more, then the surplus will be lower. Okay, and this can be seen, I think, on like this slide was not that important. I think the important part is this part. Okay, so basically if you depict, so let's say that this is 0 to W1, the 0 to W2 is representing the values of bidder 2, and 0 to W1 is representing the values of bidder 1. So when you have a first price auction without resale, there is going to be some line which is represented by basically like gamma 2 of phi 1, okay? And it is going to tell you that in this green line, whenever the value is smaller than, on the right, or lower than this green line, then one will win and one will consume. To the upper, the two will win and consume, right? So the idea is basically like, actually, this is done for a particular uniform distribution, that if you do the same for an auction with resale, then what happens is, actually, I was wrong. So what happens is that the allocation in the first stage is more, basically, is to the right. So like basically bidder 2 is bidding more aggressively. So bidder 2 is getting, the weak bidder is getting the item more often. Okay? And then with the resale part, we make this blue line to the right, which is helpful for the surplus. Okay, which is helpful for the surplus, but it will not go all the way down to here, right? So basically, like this yellow line is the most efficient allocation. So in order to get the most efficient allocation, I need to allocate to bidder 2 whenever it is to the right of the yellow line, and to bidder 1 whenever it is to the left of the yellow line. So the green line this is like the inefficiency due to the equilibrium behavior in a first price auction without resale. And here in the previous slide, this whole thing is the inefficiency due to the behavior in the first stage of first price auction with resale. This is corrected a little bit. But it doesn't go all the way down to here. It doesn't go to efficiency. And still, this part is going to be the inefficiency loss at the end of the resale stage in the first price auction with resale. And therefore, basically, whether this area is bigger than this area will be determining which auction is better. And the more asymmetries there are, this area is likely to be higher. That's why you will have like the surplus can be lower when we have auctions with resale. Do you have a question for you?
No, I guess it is still puzzling to me that this comparison that resale make FPL is worse than FPL FPA when the asymmetric inversion. So that part seems to be still a bit puzzling to me. So I may have missed.
So, but basically, like I think you can understand this either from this picture or like so. So from like let's compare two pictures.
I guess the
so let me see if this is successful. So let's say that this is like 1, and this is like 1.5, and this is 1. So the efficiency is like requires that the allocation is going to be determined by this line.
Yes.
And whereas like first price auction without resale is giving you this kind of a shape. And
Yes.
whereas like if you have 1 here and like 3 here, let's say the 3 is here. This is a good pen, sorry. Okay, so this is the efficiency line. And this is what first price auction without resale will give you, right?
Okay.
And then if you go from like this is the allocation at the end of the auction, but before the resale stage, and this is gonna be like the let's say that this is a half point. This is gonna be the half point, right? So this is gonna be after resale, and therefore like there is this efficiency loss due to okay, it shouldn't be the midpoint there. I'm confused.
Yeah. So yeah, I guess how much this
Yeah, I think
fraction,
this depends on the curvature,
is,
and
yeah.
this has something to do with curvature. At least like for the plums case, it turns out that like basically like the high asymmetries are bad for the social surplus.
Oh, yes. Oh, right. Yeah. Still, the intuition still suggests to me that well, because if you have a lot of asymmetry, I thought that well, in both FPA and FPAR, there are possible inefficiencies and that may be large. So,
So like here the statement says that the FPI surplus is greater than FPIR surplus if the W1 is greater than some value, right? So unless I made a mistake here, so that should be the result. But again, I think this is like the second thing that I promised you that I will check. So, and one thing to you. All right, so let's continue. We have 3 minutes. So there are, I think there is at least one and maybe a few more papers that actually had looked at the auctions with resale with more than 2 bidders, and it's complicated. The first complication is that, like, how are you going to model resale parts, right? So there's like optimal auctions with resale paper by Charles Zhang, for instance. They like it tries to do for more than 2 agents, and then like the question is like, let's say that there are 3 bidders and I have the object. Now there are 2 potential buyers. How am I going? What's the resale mechanism? There are many complications. But in general, like even when you consider like a simple symmetry, simple resale mechanisms, it turns out the symmetry result doesn't hold anymore. All right. And we already were aware of this. Gabor Virak had published a paper that kind of shows that we don't get to full symmetrization, but the symmetrization is going to be better than without resale, kind of a thing, for I think 3 bidders. For interdependent values, so we assume independent values. So when we have an extension to interdependent values, we actually can show that the symmetry still holds with 2 bidders, but the revenue ranking result doesn't hold. Okay, so we have an example. We also consider affiliated private values, and we can show that the conditional bid distributions are identical. Okay, but again, no results there. So all these things are like 3-4 page, like, you know, notes that didn't turn out to be a paper. Only this one turned out to be a paper. You know, this was I think published in 2000. I don't remember the year, but like now let's consider a symmetric setup. So going back to your question, right? So now let's consider a symmetric setup, but consider multi-unit auctions, okay? In a discriminatory price auction, okay? So chapter maybe, I don't know, like 12 of BJ's book will tell you that we have a symmetric equilibrium under the symmetric setup, in which the equilibrium of the bid function is given by this expression, okay? And so the allocation is symmetric, so there is no reason for resale. The answer is actually no. The answer is if in this setup, okay, so like this setup is, okay, again, to remind you the setup, we have a multi-unit setup, we have k items, we have n bidders, they all have single unit demands, they have values, this value is only for one unit, and this is coming from the same distribution, and there is a way of getting the equilibrium function, which is symmetric, so that means that the highest k valued bidders will get the item, and this is efficient. But if you allow resale, if the bidders can resell to each other, we can show that this equilibrium is no longer an equilibrium. Because what can happen is that one of the bidders can get, like for instance, let's say that we have like 3 bidders, okay? One bidder will get all 3 items by bidding very high and sell the other 2 items to the other 2 bidders. And that will be a deviation in symmetric equilibrium. Okay, so if they cannot use reserve prices, if they cannot use like an optimal auction, but will have to use some kind of like an auction that is efficient, then this remains an equilibrium. But if they can use reserve prices, this is no longer an equilibrium. The complication with this was that we were able to show the following. So we showed that when we have only 2 bidders, when we have only 2 bidders, we can show that there is an equilibrium. There is an equilibrium. Once we also assume that like the distributions are uniform, we can characterize the equilibrium. But when we have 3 or more bidders, 3 bidders, actually there exists no monotone equilibrium. Once they can use reserve prices by selling. Okay, so that was kind of like a, one little paper that we were able to publish. If you want, you can read more in the paper. I'm sorry, I only prepared 1 slide anyway. So
here, what is this doesn't talk about when there's only one unit,
Yes.
right? And if there are 2
I think it has something to do with basically like your additional benefit by selling to more than okay, so this goes back to like Garat and Troger's speculation idea. So let's say that like their econometric paper was something like this. So we have only like in the main model there is only 1 serious buyer, and then there are 2 serious buyers and 1 speculator, or 1 serious buyer and 1 speculator, and basically even the speculator who has no value for the object due to the resale possibilities kind of will bid like a real bidder, right? So I think once you have 2 objects, then everybody once you have 2 objects and everybody has single unit demand, for the one of the items, they can be a real bidder, but they also become automatically a speculator for the second unit. That's why the behavior changes.
You can resell, but you can buy only one. Then this doesn't work. Is that right?
Yeah, that's right. Yeah. So like we do not. I think like in practice, there is no banning from you getting more than 1 item, at least in some contexts. So like so the assumption here is that like you can actually get more than 1 item. And I think like I don't think we formally analyzed in the paper, but I don't think these things like this, if you do not allow for the bidders to bid more than 1 item, this will still remain in equilibrium. This should still remain in equilibrium even with resale.
Yeah, I'm still confused because about the use point, because if there's only 1 item and they just keep speculating bidder, then they'll not, this kind of things does not occur. But with 2 items, one can buy 2 things and with the expectation of resale. So I was wondering what the difference is Why does this different
Okay, I think I have a few things to think about over lunch or after, so I cannot give you a nice answer, like off the top of my head. I think if I think about it a little bit more, I will, but I don't wanna keep you from lunch, so. All right, so like in the afternoon session, we'll talk about another multi-unit auction idea, but this time no resale, but with budget constraints. And then in the second half, in the next 45 minutes of the second the session, I'm going to talk about an interesting open format that is used in some fish options, and that paper also has some experimental results too. So I hope I will have fun to present. Right, so see you in the afternoon. Thank you.
Thank you so much.